kind introduction, and it is my pleasure to introduce you to David Phillips. Before I give you a little bit of information on his background, just to remind you that David is the president of the Royal Society of Chemistry. The Society at the last count had 48,000 members, many of them obviously in the UK, and added to that nearly 4,000 school children members as part of the ChemNet organisation. So the Royal Society of Chemistry is really thriving at the moment under David's stewardship and Dave Garner's before him. And I know council and the members of the Society are very grateful for all the work and effort that he puts into helping to manage this great institution. David comes originally from the northeast of England, where I'm currently based, and he's from South Shields Grammar School, was his first school. It says South Shields Grammar School for Boys, which I think we're very grateful to know that, David. And the University of Birmingham, where he did his BSc and his PhD. He went overseas to do postdoctoral work at Austin in Texas and at Moscow, before joining the University of Southampton in 1967 as a lecturer in physical chemistry. He left the university as a reader in 1980 to become the Wolfson Professor of Natural Philosophy at the Royal Institution during the directorship of the great George Porter, Nobel Prize winner. He was acting director in 1986, and then from 1987 to 1989 was the deputy director. He took up a first position at Imperial College London in 1989 as Director of Physical Chemistry, and he was head of department from 1992 to 2002. And of course, as you will all be aware, Imperial College is one of the great universities in the UK. I saw it was very high up in the recent league table of universities worldwide. And of course, David did an awful lot to get Imperial College into that position. He was a Hoffman Professor of Chemistry from 1999 to 2006, Dean of Faculties of Life Science and Physical Sciences from 2002 to 2005, and Senior Dean from 2005 to 2006. He retains his connection with Imperial as Professor Emeritus and Senior Research Investigator, and he's a Senior Science Ambassador for schools, which again is one of his major interests, which is to encourage school children to engage in chemistry. And I think, as a lot of you will be aware at the moment, chemistry is a very popular subject out there. At my own university, our applications in 2011 are 25% up to study chemistry, and they were 20% up last year. So chemistry is a growing subject out there, and David is one of those people that is actively promoting the subject. While at the Royal Institution, he gave the Christmas lectures jointly with John Thomas on BBC TV in 1986 and 1987, and he's had many series on television and interacting with the international community. He broadcasts for TV and radio on his research interests, and he popularises science and the state of British science around the world, which again is a major role for him as President of the Royal Society of Chemistry. He now gives something like 20 popular lectures a year outside Imperial College in the UK and abroad to school children and lay audiences. So again, he is actively promoting chemistry worldwide, which is a subject, is something that we need. He was awarded the Royal Society of Chemistry Nyholm Lectureship and Medal in 1994 and 1995 for services to chemical education, and the Michael Faraday Award of the Royal Society in London for public understanding of science. He was awarded the OBE in the Honours List in June 1999 for services to science education, and he's the author of many books and publications, and he has a list of publications totaling some 590, which again I think is a measure of eminence as a member of the chemical community. And David, we invite you to give your lecture this evening.
Thank you. Well, I hope I can live up to that kind introduction. Very flattering. This is a lecture which I have used this title for quite a long time, but if any of you has heard this before, I hope you'll find some new things in it as well. It's part history of a subject, and it's also partly what I'm interested in right now, which will come later on. So I want to begin by just showing you that I am indeed a card-carrying chemist by doing some chemistry in front of you, which many of you will be familiar with. Now, I have to warn you that there might be a loud noise. There might be. So here we have a mixture of gases which have the capacity to react, but they're not reacting at the moment because I have to provide some energy, in this case an activation energy, in order to produce a reaction. So I'm going to do that in the form that most people would be familiar with. I'm going to provide some heat. So here we go. Everyone's still alive. I was told that somebody had a heart attack once when not me, somebody else did something like this. Well, you may notice I have another one of those. You've probably all had a long day. If I see anybody nodding off, I won't hesitate to use it. However, the main point of doing that was to show you that this chemical reaction was initiated by heat. But the kind of chemistry that interests me is not initiated by heat, it's initiated by light. And light is a very convenient form of energy. Just to demonstrate to you that light is a form of energy, I have a... This thing seems not to be working terribly well. Okay. Is it all? Can you hear it at the back? I have a very feeble torch here, and I have a device made by BP, so I don't take this to the southern United States. And you see that when I put the light on, can you all see it whizzing round and round? So the only energy that's entering that is the solar, is the light from this little torch, converted into electricity in the solar cell, and then driving a little electric motor. And if I take the light away, you'll see it stops. So there's no question, I think, that light is a form of energy. It's actually very easy to make light. And so I can demonstrate that with a little device here. And here it would be helpful to have the lights down, please, if we can. This is just a little toy, a plasma globe, where we're passing an electrical discharge through a gas, exciting the atoms, which are then emitting light. If I put my finger on the top, you'll be able to see that the stripe, this thing is intermittent. I don't know what's wrong with it. The stripe which goes to my finger is much brighter than the others. And so reason would tell you that since it's an electrical discharge, they must be... I think this mic is... Is it still going on? It's okay. Yeah? So there must be more current going down that pathway than any of the others. And that can only be if I'm acting as an electrical earth. So the current must be flowing down my body and into the ground, and yet I'm still standing here. Now, you know very well if you put your fingers into an electrical socket, it's the last thing you'll do. So the current must be very tiny. So it's not a very efficient form of light, but you're all familiar with these things. This is just an ordinary fluorescent light tube. And you can see that if I put it anywhere near, it lights up. All right? Now, these things don't light up spontaneously. There must be an electrical current going through there. And so, again, since I'm quite happily standing here, it must be a very small electrical current. And if you finally wanted any proof that I'm telling the truth, if I hold it halfway down, only half of it lights up, okay? So it's very easy to make light efficiently. But I'm interested in what can you do with it, what can you use it for. And I could tell you that the reason you're here is because of sunlight, of course. We owe everything to sunlight. But there are many lectures in that, and I'm not going to deal with those. I think that most people are interested in their own well-being, their own health. So this lecture is about how light and lasers is used in medicine. but from a chemist's point of view. So the story begins really with this gentleman. His name is Niels Finsen, and he was a Danish physician. This keeps going on and off, so it's coming up, okay. So I'll just keep going, right. Niels Finsen was a Danish physician. He was also an amateur scientist. He, in the late 1880s, noticed that people who had tuberculosis, where you suffered terrible facial sores, fewer of these sores were exhibited in the summer months than in the winter months. That was the observation he made. So he reasoned that maybe sunlight was curing the sores of these people with TB. Yes.
It's the technology batteries.
Okay, can you all hear me now? Yeah, fine. I'll just shove that in my pocket then. Right. So he had made this observation that maybe sunlight was curing the sores. So being an amateur scientist, he decided to do an experiment. And he got hold of a patient who had some sores, and I won't ask for a volunteer. Here's my patient that has terrible facial sores. And he got hold of a newly available carbon arc lamp, and here's my very old version of that. And he simply focused the arc lamp onto the face of the patient with that kind of result, in fact. The experiment was a total disaster because he did not cure the sores, but he did give third-degree burns to the patient. Well, you know, a lesser man than Finsen might have given up at that point, but he reasoned, what had he been doing? This is an incandescent light source, so the color of light, the spread of wavelengths you get, depends on how hot it is. And in his particular case, and in the case here, if you look at the visible spectrum, almost all of the radiation coming from that lamp is in the infrared part of the spectrum, which is off that end of the slide. There was some visible light, as you saw, and there was a tiny amount of ultraviolet A radiation as well. So he decided to do a second experiment. It's very easy to get rid of infrared simply by passing light through water. Just as an aside, you may all know that carbon dioxide is a powerful greenhouse gas, but it is not the greenhouse gas which keeps the planet as warm as it actually is. Water vapor is the main reason why we have this blanket. We can't do anything about the water vapor, so we worry about the carbon dioxide. Quite rightly so, but you need to know that it's water which is important. So, pass radiation through water, the infrared disappears. So he did a second experiment where he somehow or another managed to persuade another patient to go through this. And here he put a water vessel, just a glass vessel with water in it, and this time partial success. He didn't cure the sores, but he didn't burn the patient. So he was getting there. And then he realized that, of course, glass doesn't transmit ultraviolet light. And so maybe it was the ultraviolet. So he did a final experiment where he used a quartz vessel, which does transmit ultraviolet light, and this time success. And the patient is shown here. You see that model wasn't so silly after all, because this is what the sores look like on the face of the patient, and this is what the patient looked like not long afterwards. The sores dried up and the scab dropped off, and so she wasn't cured of the TB, but she was cured of the sores. Now you might imagine she'd be smiling broadly now, wouldn't you? She's a Scandinavian lady, and they tended in those days not to smile too much. And if you want any evidence of that, just read some Ibsen, and you'll know all about that. So photomedicine really was invented by this man, Niels Finsen. And it sounds trivial, But for his invention, he was awarded one of the first Nobel Prizes in medicine in 1903. So the world at that time thought this was important. So here are the effects of the definitions of photomedicine as it's currently practiced. It's the effects of light on the skin. The skin's the most accessible organ of the body. It's also the heaviest organ of the body. It's the use of light to diagnose medical conditions. It's the therapeutic effects of non-laser light, and it's the use of lasers. And I want very briefly to go through these, in some cases quite quickly because we don't have too much time, and I want ultimately to concentrate on areas where chemistry has actually made a big difference. So let's look at the skin first of all. There is some chemistry here which is interesting. It's the production of vitamin D. The definition of a vitamin is it's something that you have to have in your diet which you cannot synthesize in the body, and this is the exception, if you like, because you can synthesize vitamin D through the action of sunlight on the skin. And if you don't have enough vitamin D, then certainly children would develop the condition rickets, where the bones don't form properly. And you have here 3 children. The 2 on the outside have rickets where the bones are deformed, and it's irredeemable. Once it's happened, you can't recover from it. So it's important you have enough vitamin D, certainly in early childhood. Well, we tend to get enough vitamin D now in our diets. Interestingly, though, it is becoming a problem in northern UK amongst Asian populations who cover themselves up and do not get very much sunlight, that there is evidence now of rickets reappearing, and easily diagnosed and easily treated, but interesting that it is once more rearing its head. Next one, tanning. Well, we all have experienced that, and it doesn't matter what color your skin is, you will experience tanning. The darkening of the skin, where the melanin in the skin takes on a darker hue. We should recognize it's a protection mechanism against the harmful effects of ultraviolet light. Although I put a plus there, meaning it's probably a good thing, that's because when we tan, usually we're doing something nice. We're on holiday or we're playing tennis or whatever it is. But actually the skin recognizes that this is a problem and tries to prevent the harmful effects of ultraviolet, which include aging and skin cancer. Now I want to go through this very quickly. I'll forego the experiment where we all have a mass experiment to see how good our skin is, because with an audience of, well, it is a mixed audience, but it's much better done with children, so I won't do it. Many of you in this audience will actually know who that is. When you talk to young children, they have no idea who that is, or is the right word, she's still alive. But that's Brigitte Bardot, who, when I was 17, sort of quickened the pulse of most young men. And that's what she looked like. And what does she look like now? Well, she looks like that. And young children find this disgusting. But I'm very pleased to be able to tell them it's going to happen to them as well. And it's only the speed with which it happens which they can change. If they do not want to age their skin, they should stay out of powerful sunlight or use sunscreen. So the message is pretty plain. Now we're going to come back to skin cancer at the end, because that is, of course, a very sinister effect of ultraviolet light. And I want to talk about how we might treat it using photochemical methods. Let's turn to diagnosis. It's not so long ago that you would only seek medical treatment if you had some obvious symptom, an ache in the gut, a fever, a pain somewhere or other. But many of the conditions that we now suffer from are microbial in origin, and well, not just microbes, proteins can cause the same sort of thing. And so if you were able to diagnose that you were carrying the agent of disease before the symptoms develop, you could treat before you have any really harmful effect. So this just gives a simple example of the principle of immunometric assay, immunochemistry as widely practiced. So here you take an antibody which is specifically looking for an invading molecule or organism, which is called the antigen. And here is the antigen. So you immobilize one antibody on the wall of a vessel, a test tube if you like. You add a sample that you've taken from a patient, might be blood or urine or all sorts of other things. And if the sample contains this antigen that you're looking for, it will bind to the antibodies that are immobilized. And the trick then is to add a second antibody which will bind to another binding site on the antigen. So these yellow ones, or whatever color they are, won't bind to the blue ones, but they will bind to the brown ones if they're there. So it's a positive reading system because you label this in some way, which you can then measure. Now remember, we're talking about molecular levels here. These are tiny amounts of material that you're looking for. So the label used to be radioactivity, but that has its own problems dealing with. Nowadays, one simply uses light, and there are various forms of light you could use. One of them I'd like to show you, and so I do need the lights right down for this. And this is chemical light. So let me just move that into the middle. Well, actually, I'll put it there. I'm just going to pour two chemicals together and make some cold chemical light, which I'm sure you've all seen before, chemiluminescence. Not very bright, it's not very strong, but you can get commercial versions which are much better, so I brought a few of those along. And some of these are quite old, so they're not going to work, are they? No, that one didn't work either. Ah, that one did. So I'll throw that over there so you can pass it round. Another one of the same color, so we can just have a look there without... I didn't put on the hazard list, throwing things out. Pink one, we can just pass it behind and see. And there's a socialist one here, if anybody wants it there. Okay. So, this is very bright. Some of you may know, it was said earlier, this is the International Year of Chemistry, and we launched the UK version in Parliament at the end of January. And David Phillips is a beautiful photograph of the Science Minister actually doing one of these chemiluminescence experiments in the House of Commons, which we're quite proud of. He didn't give us any more money, but never mind, you know. So, what can you use this for? Well, here's one example. Diagnosis. You can diagnose pregnancy very, very early on, looking for that hormone, human chorionic gonadotropin. We have a specific antibody which will look for that hormone. So extremely early on in pregnancy, not quite as early as shown in that slide, but not long after this, you can detect pregnancy, and quite often that is really very important if you have a blood mismatch or whatever. So that's one of the things you can do. But you have other forms of luminescence you could use. And so I have over here, and again we need the lights down to see this, a whole variety of, these are actually just laser dyes from the lab. This one's quite interesting. It's diphenylanthracene. It's colorless, so it has no color, but all molecules have electrons, and so when light falls on, the electrons jump from one orbital to another, which is all that happens in light absorption. And then when the electron jumps back again, it gives out the light. But the light is of a different color than that absorbed. This is absorbing ultraviolet and giving out blue. And you can get any color you like depending on which dye you actually use. And so they're all very pretty. Now, if I can have the lights up for just a minute, you may wonder what this is doing here, but it's to keep the malaria down, you know, is what it's for. This is just ordinary tonic water, which I'll pour out. And whereas I would hesitate very much to drink this, it's diphenylanthracene, it's a carcinogen, it would give me cancer. The solvent is methanol. This is just tonic water, but to show that I'm not cheating, I'm going to drink it. You may be surprised to see it has a bright blue fluorescence. Dip the lights for a minute, you'll see that. So I'm going to drink it just to show it is tonic, but if you will forgive me, I'm going to add to it. We call that solution T. This is a little solution G, which I'm going to add, which does not fluoresce, but renders it palatable. And I never fake experiments, so this is for real. And I once gave a presentation like this 5 times in a row, and I had no idea what I was doing at the end. You're very good health, and thank you for coming. One of the few perks a president gets, you know. So you may have seen, if you looked at that carefully, that there are all sorts of things that fluoresce. You see dandruff fluoresces quite nicely. If I grin at you hideously, my teeth fluoresce. I'm just showing off. I still have my own teeth. There are all sorts of things fluoresce in the body naturally. And if you're trying to look for tiny signals from an immunoassay, you have a problem because the signal you're looking for is masked by the signal which comes from the autofluorescence in the body. You can get over that by using a fluorophore which is longer lived than the fluorescence of the body. The fluorescence in the body lasts for about 4 billionths of a second, 4 nanoseconds typically. These dyes, you see, apparently extinguished immediately. They live for about 1 billionth of a second, 1 nanosecond. But something like this, if I irradiate it, lasts for a very long time. Can you see it's much longer? Now, this isn't a true phosphorescence or true fluorescence, so I'm cheating, but it is the sort of technique that is used. You use as a label something that lives longer than the thing that you don't want to see. And by using a pulse laser and a timing device, you can actually measure the thing that you want to. So fluorescence has become enormously important in biology and in medicine. And what has really revolutionized microscopy is the development of green fluorescent protein, for which a Nobel Prize was awarded 2 or 3 years ago. I can't quite remember. So it came originally from a jellyfish. It has the capacity, the gene for it can be expressed in any organism. And you can label any part of any living organism the way you want with this particular material. So you can look inside cells and see how cells operate by labeling with this fluorescent material. You can label specific proteins. It looks like that. We're not going to worry about that. But the active ingredient is a trimer. It's 3 amino acids in a particular sequence. But actually it isn't, because when you shine a light on it, there's a chemical change, a photochemical change in that sequence, which is what gives rise to the emitting species. So what do we use it for? What can we use it for? I'll tell you what we use it for. And a little aside, this was a piece of equipment that was developed by the physicists, the chemists, and the biologists in Imperial College for a particular purpose. It's based on femtosecond lasers, very fast lasers. It was an original microscope. It cost the Engineering and Physical Sciences Research Council something like £750,000 to develop this as a prototype, if you like. We still use it, in fact. By the time we had completed this project, you could buy these off the shelf commercially. We were overtaken by the speed with which the medical and biological sciences professions realized how important this development was. But that's our version of it. And what do we use it for? Well, we're interested, one of my biological colleagues are interested in the immune system. And here you have this is a cell, any cell in your body, and all the cells in your body present on the surface all of the time the proteins which they are synthesizing inside that cell. And that's interrogated. They're presented through this apparatus called the major histocompatibility complex. And this is a T cell, part of your immune system, which is interrogating those proteins. And if it finds a protein which shouldn't be there, then it will kill the cell. The cell will be killed. So that's your first line of defense. But there are some viruses which have learned how to remove the apparatus which presents the proteins. So no proteins are presented, so the T cell can't see anything, so it lets this cell live, inside which, of course, the virus proliferates. And so your second line of defense is a natural killer cell, which looks for the apparatus, not the protein. And again, if it doesn't find the apparatus, then that cell will be killed as suspect. And so what we have done, and I'm not going to give you details, is to look at that interaction between the receptor and the complex, using labeled proteins to see exactly how this works. How does it interrogate the two halves? And it's a piece of biology, and I'm not a biologist, so I'm not going to try and explain it to you, but it has been remarkably successful. And what has made that possible is the development of this natural killer, of the green fluorescent protein, and also the development of very sophisticated laser-based techniques for looking at fluorescence. But what you're measuring is exactly the sort of thing I've just shown you, simple fluorescence from simple molecules. Well, I want to move on rapidly to talk about therapy. Here are some of the examples of the uses of light to treat disease. Psoriasis, vitiligo, they're not related, but psoriasis is a disease of the immune system again, which leads to a rather nasty rash on your skin. Each of you makes skin cells in the basal layer of the skin, which are globular when they're produced, and they travel towards the surface, getting flatter and flatter as they travel. And by the time they reach the outside of your skin, they're dead, and they drop off. And most of the dust in your houses and on the tube, if you travel by tube, are actually the dead skin cells of the inhabitants of the house, which are much loved by little creatures which eat them. So, you know, we're not alone in the house. We have all kinds of fauna which enjoy the fruits of your shedding of your skin. Well, if you have psoriasis, the skin cells are produced at too fast a rate, and so they move to the surface. It takes 28 days in a normal person. They arrive much more quickly than that, and so they're not yet dead when they arrive. And you can imagine how that must feel if you've got kind of living skin on the outside instead of dead skin. Very uncomfortable. Not life-threatening, but not very pleasant. And the treatment that was discovered, I'll describe in just a minute. So that uses ultraviolet light. The next one, which I will talk about in some detail, uses red light. Jaundice, which is what I'll finish off with, uses blue light. I won't talk about white light, winter blues, but it is effective. And I'll talk a little bit about laser surgery. So let's just go back now. This is the psoriasis. This is what it looked like on this particular man. Very, very nasty example of psoriasis on his back and legs and backs of his arms. A dye was chosen which, not unlike this one, it absorbs ultraviolet light and turns on some chemistry which destroys the skin cells. And the skin cells drop off, and the skin for a while underneath is perfectly normal. But you have to have this treatment repeatedly in order to, because you're treating the symptom, not the cause of the disease. Vitiligo, might need to dim the lights a little to see this properly, is really just the loss of pigmentation from the melanocytes, the pigmented skin cells. Not life-threatening at all, but very disfiguring if you happen to have a pigmented skin. Same treatment, you destroy that outer layer of skin, and for a while the skin is normal underneath. So that's vitiligo. The effects of lasers depend on the tissue and also the intensity of the laser. This, obviously, in my hand is a small, few milliwatt laser. At that sort of power, you get what's called biostimulation. Cells divide more readily than in the absence of the stimulation, and that's used for wound healing. misgiving about whether that happened or not in the West, because it was developed in Eastern Europe for treating battlefield wounds, in fact. But it's now commonly believed that it does have a positive effect. Above the power of this laser, certainly 10 times more powerful, you get biosuppression, the exact opposite. Cells don't divide as readily. Around 40 watts per square centimeter, you get, in the presence of an absorbing dye, you get photodynamic therapy, which I'm going to talk about. At 400 watts per square centimeter, that's a pretty powerful laser now. You get coagulation, which is just the medical term for cooking. And around 4,000 watts per square centimeter, you get vaporization. The tissue just disappears. So, all of these lasers are used in medicine. And I'll just summarize. Infrared is used as a cutting device. It's for soft tissue laser surgery. And it can be either carbon dioxide or erbium YAG or neodymium YAG. Ultraviolet is widely used, and you all know about this because you see the ads, to have your eyeball reshaped in order to correct whatever vision defect you might have. It's an ultraviolet laser which is used, which just ablates the tissue. The tissue just disappears. So what happens is that if you have too much curvature on your cornea, they will sculpt away the middle of the eye to make it less curved, and therefore you can focus on the retina. If you want to go the other way, you've got to take away tissue from the outside of the eye, but it's perfectly doable and is very common. Diode lasers, that's used for photodynamic therapy. Femtosecond lasers is used for 2-photon excitation. I'll mention that very briefly. And then you have the cosmetic uses. Now, some of this is science, some of it is pseudoscience, some of it is pure adman. But you will see advertised various lasers using all of those above, plus the ruby laser and the alexandrite laser used for hair removal, teeth whitening, acne, tattoo removal, stretch mark removal, that only applies to some part of the audience, pigmentation removal, and treatment for aging skin. And I would not wish to stand here and say that all of that works. It has one very profound effect. It lightens your wallet, but whether it cures you is some other question. So let's look at, very briefly, some of those. This is one of the first uses of lasers in the Royal South Hants Hospital in Southampton. This is a pigmented skin for a port wine stain. A laser was used of the similar color to the one I've got here, and you see the effect immediately after just one treatment is looking good. Being an English lady, she's starting to smile, you see already. Cutting, this is soft tissue surgery again. You use an infrared laser, which I've already said, water absorbs, and so you get a tremendous amount of energy deposited, which makes it into a cutting device. And it's a bloodless cutting device because it cauterizes as it cuts. So here you have, this patient has a rather nasty tumor in the tongue, which has to be removed. If you feel squeamish, don't look at the next slide, because you see that's turned on its side, in fact, but you see that tumor being removed bloodlessly by a carbon dioxide laser in this case. The good news here is that's what was removed. That's the tumor. Notice how big it is. This is in inches because it was made in the United States of America, as you see. And the really good news is that here's the same tongue 6 months afterwards. And this patient lived for 6 years afterwards, so went well over the boundary of being said to be completely cured. So that was a good news story. Here's another. I'm sure there's nobody in this room who's foolish enough to smoke cigarettes or anything else for that matter. But if you do, you stand a much enhanced chance of dying a pretty degrading death. And so here is a patient from the University College Hospital in London. This is the trachea going up to the mouth. These are the two bronchi that go down to the lungs. This is a tumor growing as a consequence of cigarette smoking at the junction. This branch is completely blocked off, no air going down to that lung. That tiny little passageway is there is the only way this guy can breathe. He was in a terrible state, on oxygen, miserable quality of life. A powerful neodymium YAG laser was used just to blast away that tissue, and you see the effect there, nice clean bronchi, the guy could breathe again. He was dead within 6 weeks anyway, because by the time you exhibit the symptoms of lung cancer, you will invariably have secondary tumours elsewhere in the body, which is what will kill you. It gives the symptoms very late in the development of the disease. Well, that's not really chemically interesting. I mean, there is some interesting chemistry there, but it's not really discovered because all the medics are interested in is, does it work or not? And it does. This is chemically interesting. This is photodynamic therapy. And it's the use of a dye sensitizer plus red light to treat cancer and also to destroy bacteria and viruses and, in some cases, fungi as well. So how does it work in PDT, in the laser, the cancer treatment? Here we have a cartoon which shows a patient. You inject the dye into the bloodstream and it travels throughout the body. Within 2 heartbeats, it's throughout all of the blood vessels in the body. Now, improbably in this cartoon, the artist who made it for us located the tumor in this guy's leg. Actually, it's almost certainly, we only ever use the treatment for the hollow organs, for the alimentary canal or as you'll see, other hollow organs. So you have to try and imagine that somewhere else, not in the leg. So these dyes are chosen so that they accumulate preferentially in tumor tissue. So if you wait a little while, there's more dye in the tumor than there is in the normal tissue surrounding. So then you put a red laser into the body. That excites some chemistry. These are porphyrin-type molecules, or phthalocyanins. You pass on the energy from the porphyrin to oxygen, which in its normal state is a very unusual molecule. It has 2 unpaired electrons, a triplet state, and it forms this species called singlet oxygen, which is hugely reactive. It will react with anything around it, and in fact is the cytotoxic species. This is what destroys the tissue surrounding. So that turns on the killing machine, if you like, and so you destroy the tumor preferentially. If the dye is only in the tumor gets destroyed. So it's preferential treatment. So does it work? Well, it does. If any of you are interested in the chemistry, that's just what I said. The dye absorbs light, becomes excited. It can give out its energy as fluorescence again, so you can see where it is. That's an important thing. And then it crosses to this long-lived state, which is the one which produces the singlet oxygen, which then destroys the tissue. So here's a guy who's been targeted. Oh, incidentally, I said you have to use red light. Why red light? Well, I think it's best if we have the lights right down for this. This is a white light source. This is all colors of the rainbow. If I put my fingers over, can you see that only the red light is transmitted? Right? Human flesh transmits red light, but it does not transmit any other color. So if you want to get light into the body, you have to use red light. Anything which absorbs red light looks blue or green. So dyes are blue or green, and I have some examples here. This is a phthalocyanin, and can you see it has a kind of blood red fluorescence? So you can track where it is just by looking for that fluorescence. And being clever chemists, we can make it dissolve in this case, in fat, get this right, in water, or can dissolve in both, and it's actually the one that dissolves in both which is the most effective. So that's an aside. So, here's a targeted fellow. They really do turn the color of the dye that you inject, but not as obviously as that. Here's some fluorescence. These are rodents who have been injected in the base of their tail, and this is not a tumor-bearing mouse. This is just an ordinary mouse. Is it a mouse or a rat? I can't remember. It's a mouse, I think. So you inject there, and There's no fur on the ears or the tail, so you can see they're fluorescing quite nicely. But in this case, the rest of the body would fluoresce. The idea is to use a dye which is only in the tumour, so you can spot where the tumour is. They hate being injected in the base of their tails. They really don't like it, so we resort to trickery, as you can see. Let's just turn to treatment, which is very commonly used now throughout the world. 3 forms of skin cancer. The basal cells, the ones that are first formed, do not metastasize. That is, they don't spread to other parts of the body. Squamous cell, they're the ones on the move. They very infrequently metastasize. They stay local as well. Melanoma, which is the cells which have the pigment in them, are deadly because they metastasize within just a few weeks of the melanoma forming. So secondary tumors develop extraordinarily quickly if you happen to be unfortunate enough to get a melanoma. So if you ever see anything like that on your body, go and get treatment immediately. That's what it would look like. That's a melanoma blemish. And it's caused by sunlight, so excessive exposure to sunlight will cause this. So here we have a patient who has a basal cell carcinoma, which will not spread elsewhere in the body, but will get bigger and bigger unless treated. Conventional treatment would be surgical. You dig deep and remove all of that tissue to make sure you've got all of the tumor removed. So she'd lose the bridge of her nose, she might lose that eye, she'd be disfigured for a long time afterwards. What was actually done was to use that very dye I just showed you there, injected in the body, and irradiated for about 30 minutes, single radiation with red light, and a few months, 6 months later, that's what she looked like. You can hardly see any scar tissue at all. Really tremendously successful. Now, she should be smiling broadly, shouldn't she? But she's a Russian lady. They were done in, these tests were done in Russia. And at that time, they didn't apparently smile either. So. Now, I just want to make men uncomfortable. While you contemplate that, you've got to get light in the body, so how do you do that? You use an endoscope, and this is a very old-fashioned endoscope, which is why I've got it, because it's no longer used in the hospital. This one is actually a bundle of about 10,000 individual fibers, down which you can put light and you can see where it's inserted. This is actually a gastroscope. This goes down your gut as far as your stomach. I want somebody to imagine that it is in, maybe you would do this for me, just hold it up so people can see. So this is now in your stomach, all right? And I can look down it, I can steer it in any direction I want. There are others which are bigger. The colonoscopes, of course, are rather heavier duty than this, and if you imagine doing that, it brings tears to the eyes just to contemplate, doesn't it, really? In this case, it's a rather smaller version of this, which is being inserted into this patient's bladder, again in University College Hospital, where with whom we collaborate. And this guy has a form of bladder cancer which doesn't metastasize. It's not going to spread, but it continuously grows in the bladder. The before and after don't look too different. That's the tumor growing on the wall of the bladder. This is after it's been treated by exactly this treatment. It's now all dead, and that tissue just sloughs away and is excreted in the normal way. And so pleased is the patient. He's quite happy to look down into his own bladder and see he's smiling broadly at the result. Well, I'm not trying to oversell this, but we really do believe this is a remarkable development of applied chemistry, if you think. Here is a very nasty, aggressive tumor growing under the tongue. Surgically, that patient would lose all of the tongue, would never speak again, might lose some of the floor of his mouth. I mean, it would be a really brutal treatment. Photodynamic therapy did that. Destroyed the tissue, destroyed the tumor. This is 3 weeks afterwards, and 6 months afterwards, perfectly normal tissue in the mouth. So a really excellent way of getting over the brutal surgical treatments that are currently used. Now, what we want to do, I've got to make sure I don't go too long, I probably am already, is to try and achieve targeting. How can you make it absolutely specific to the tumor and nothing else? And I'm not going to stress this. What we do is we use a monoclonal antibody fragment which specifically targets the tumor, and we attach to it the dye stuffs that we want, and we can get as many as 10 dyes onto this molecule. And then when we irradiate, this is a mouse, it's a human tumor in a mouse, you could see that this is just the free sensitizer. If we inject what I've already showed you more or less, this is how much better it is if you actually target. You actually completely destroy these tumors fairly quickly. And this is done through a small company that we developed 7 years ago, and is now, we've got to the stage where we want to now do clinical trials on this targeted photodynamic therapy. I'm going to forget that one and just finish on this one. Any of you know that you had jaundice when you were born? Several in the audience will have done, and many of you will have had the treatment. It was discovered by this lady, Judith Ward. She's an Essex maternity nurse. Here's my nephew undergoing his treatment. I'm sure you see there's a strong family resemblance there. The treatment that she discovered was simply that you bathe the baby in blue light, and that cures the jaundice. And it can be very serious. It can cause death if not treated. So I'd like to finish by showing you a baby having the treatment. And here he is. He's my pride and joy. He's everywhere with me. He's quite old now, but we won't go into that. And also he gets damaged when we travel around, as you'll see. Well, the important thing about him, notice I call him him. You'll see that there's no question as to the gender of this child. Male baby. In his legs he has the authentic material which causes jaundice in newborn babies, bilirubin. It's a breakdown product of red blood cells. And he can't excrete it, as you can, because you all have an enzyme in your liver and bile which renders this material water-soluble, so you can get rid of it. He can't, because it won't dissolve in water, so I'm going to give him a drink of water. He drinks through a funnel, so I'm just going to pour that in. And when I hold him up, he will be the water will be the top layer. That should do. And I hope you can see that the water layer is still colorless liquid, the bilirubin is still in the legs. This is in a fat solution. You have a lot of fat just under your skin. That's where the material goes, hence the jaundice. So to cure him, all I have to do is irradiate with blue light. Enough blue light in there to do this. This takes just about 2 minutes and then I'm finished. The chemistry is really interesting. It's been disputed for a very long time. This was discovered in about 1955-6. The chemistry really was elucidated only a few years ago. And what is actually happening here is, for the chemist in the audience, a cis-trans isomerization reaction, which you can only achieve photochemically. You cannot do this by thermal chemistry. It has to be light that does it. It's exactly the same kind of chemistry which takes place in your retina, which gives you the vision process, a cis-trans isomerization, which again can only be done with light just as well, because if you could have a sensation caused by thermal effects, you would have permanently fogged vision. It wouldn't really be a vision process. So we're cis-trans isomerizing about a double bond, and now I have to do something I wouldn't dare do in Massachusetts. I have to shake him violently. And even that short irradiation should be enough to have flipped the molecule around, which opens it up. It presents the carboxylic acid group then to the water, and it becomes water soluble. And you'll see it has indeed become water soluble. So now little bobbit. Little bobbit, as I call him, can do what nature intended and what you all do, although those of you, the half of you whose physiology resembles this, he can remove his bilirubin, and I hope you can now see why I call this presentation a little light relief. Thank you.
David, thank you for an excellent lecture. I'm certain you will take some questions. We have microphones, so if people can wait till the microphone arrives and then obviously speak into the microphone and get your question across. Lady here. If you could stand up and say who you are and where you come from, please.
I'm Jennifer Goldsmith. I've graduated in chemistry with the Open University. Will PDT be used in future to kill metastases in cancer, wherever those metastases may be?
You're really asking, can it be a systemic treatment? The answer is probably not, because you need two things really for it to work. You have to have the dye where you want it to be. Now, we can certainly target metastatic cancers and tumorous materials traveling throughout the body. What you cannot do really easily yet, and maybe you can in the future, is to provide the sufficiently high light dose throughout the body in order to have enough intensity to actually kill things which are away from a solid tumor, if you like. Now, there have been some treatments in the United States which have tried to do that with partial success, but you have to be extremely careful, and the reason is that the dyes are normally excreted through the liver. So a normal liver will be heavily dosed with these sensitizing dyes, and if you irradiate the liver, you'll knock out the liver and the patient will die. So systemic treatment, you have to find a form of systemic treatment which would protect the liver. And so far that hasn't been terribly successful. But on all kinds of localized tumors, it is very, very successful.
Any other questions for David?
I'm right at the back there.
I'm Richard Fort for the Royal Society of Chemistry. David, how much of your work is curiosity-driven, or are you targeting specific diseases with your work?
That's a good question. The first half of my research life was purely curiosity-driven. I was interested in why molecules, when you excite a molecule, some do one thing, some do another, some fluoresce, some cross to the triplet state, and I really was interested in trying to understand the structure relationship that a molecule had and its photochemical fates. So that was pure curiosity-driven. But when I moved to the Royal Institution in 1980, there was a move afoot, if you like, then with the funding councils to look for exploitation of research, of basic research. And so I never gave up doing curiosity-driven research, but I also started to dabble in this particular field, which was obviously had a not a commercial end, but had a medical point to it. And I've kind of stayed with that ever since, so that now all of the research I do, which is not much because I'm sort of semi-retired, is this applied research, if you like. I've stopped doing the curiosity-driven research, partly because you can't do everything, and the kind of things that we were doing before require really huge expenditure on equipment. And although I think I could have generated some of that, it would have been at the expense of younger people trying to get those fundings. And I thought, it's their turn, I shouldn't be competing to do that. So the short answer is there are still some things to be explained in this area, And so, you know, there is a kind of curiosity element to it, but actually this is mainly applied.
Maybe I can ask a question. I think with the recent closing of the research centre of Pfizer, then it's just highlighted again that the public's perception of the chemistry-medicine interface is still very much drug discovery. And it's only when we get listening to lectures from people such as yourself that we suddenly realise that the chemistry-medicine interface actually goes way beyond that. Is there something more we can do to actually get the public to realise that the chemistry-medicine interface is really very broad brush? Because this is not the sort of thing that gets into the public perception.
Well, it is very broad, and also a lot of it is accidental, and that's I'm not disparaging that. I mean, let me tell you how I got into this. I was, at the time, interested in using those dyes that I showed you there. I was on a project working for Unilever, and Unilever were interested in developing a washing powder formulation which would work at low temperatures, because many of their markets in the Far East didn't use heated water, they used cold water. Now, detergents work perfectly well in cold water formulations, but stains are not bleached. The bleaches that we used commonly had to be high temperature, so you had a problem. You had perfectly clean garments coming through the washing machine, but they still had stains in them of various sorts. So they were looking for some way of using the habits of people in the Far East, which would nevertheless bleach their clothes as well as clean them. And what did they do? Of course, they washed their clothes using a detergent, and then they hung them out in the sunshine. So we wanted something which would photochemically bleach the stain, and that's exactly what that stuff does. And that's how it was originally developed. Well, when we were developing that, I happened to meet by accident in the Royal Institution a surgeon from University College London, Steve Bown, and he told me that he'd read a paper where you could do this very thing and start killing tumours. And so we said, wouldn't it be fun if this stuff that we'd developed actually had that effect? And so we did the experiments, and lo, it did. And so we've been working on it ever since, in a much more sophisticated way now, of course. But that was just a chance meeting of two people who happened to develop something which works. But Mike's right. I mean, the application of chemical knowledge to medicine is far more widespread than people realize. And I was at the launch of the International Year of Chemistry in Paris at the end of January, and heard a stunning lecture by one of our own people, Dave Allen, from GlaxoSmithKline, who said that for the last 30 years, essentially, the medicinal chemists in every pharmaceutical company in the world have been barking up the wrong tree, because the holy grail is that in order for a medicine to be truly effective, it has to dissolve in the fat in the body, in the cells. It has to be liposoluble. So everything they make is liposoluble. But where most drugs fail, and very few get through into the marketplace, where they mostly fail is they have side effects, which is what kills them, because they do something that you didn't want to happen. And sometimes that's discovered very late in the development. That's why they're so expensive. And when you think about it, it's hardly surprising. If you make something dissolve deliberately in the fat in a cell, it's bound to interfere with all kinds of biochemical processes which are going on. It's bound to have side effects, because it's there. You've deliberately put it where it can have the maximum side effect. So he was saying what they should have been doing is trying to target in a quite crude way. If they made it not so liposoluble, but partially water-soluble, amphiphilic, or just change the solubility ever so slightly, they might lose something in the efficiency of the drug, but they'd gain hugely by it not being have these side effects. And to hear somebody from the drugs industry say that, that actually simple physical chemistry was something they ignored, and if they hadn't ignored, they would have been much better off. And that's what they're now doing, of course. So I'm not going to make the claim that medicine is applied chemistry, but I could partially make it.
Do we have any more questions for David? Alan. Alan.
Sorry, just a quick question on skin cancer or related to skin. Something I've come across recently, I do a lot of driving, and one of the questions that came up was, what's the difference between using a tinted windscreen and a normal windscreen? Are there any special applications, for example, for protection of the skin?
The kind of ultraviolet light which causes skin cancer would not penetrate through a normal screen. So I think it's probably a marketing ploy. I mean, I don't believe that you can get tan by sitting behind a windscreen. Well, and the wavelengths which cause the cancer are actually shorter again than the UVA tanning wavelengths.
The question was related to if you have not a normal window.
Yeah.
Sorry, not tinted. Would you need to use a sun cream or something like that?
If you sit behind a normal window, you cannot get suntanned. The ultraviolet does not penetrate. So the idea of having a UV tinted window on a car, presumably, is I suspect just a marketing ploy to think. You may think you need it, but I doubt seriously you do.
Thank you. My thoughts.
I mean, there are all sorts of coatings which are reflective, which lower the heat burden inside the room, and they work and they're good. But in terms of health protection, I don't think you need worry.
I thought it was a bit of a strange question. That's why I wanted to clear up my own mind. Thank you.
My wife suffers from skin cancer. She spent a lot of her youth out in Singapore and obviously got a lot of sunshine, and that's now something that's coming back to haunt her. And she has to have these creams which actually essentially burn the cells out. One thing you didn't comment on was the ability of radiation to penetrate through the skin and how far it can actually get through.
Good question. The PDT is best if you get the tumours very early on, because the penetration depth depends which wavelength of light you use, but typically a penetration depth might be 4 to 5 millimeters, which is not very big. So if you've got a big solid tumour, it's not the ideal mechanism for doing it. If you've got a small tumour just growing, it's the ideal thing to do because it's non-surgical and it will destroy the tumour. So how do you get around that? Well, the first lasers that we used, the first treatments for PDT, used light of just over 600 nanometers, which is just a bright red. But that doesn't penetrate very far because the tissue absorbs. Much better if you go further out into the infrared, in fact, just into the near infrared, but then you can't see it, so it has its own problems. So the ideal wavelength is just about on the boundary of the visual process, so you can see what you're doing, which is around about 700 nanometers. And at 700 nanometers, you'd get a penetration depth of several millimeters, depending on the tissue, but up to about a centimeter, in fact. So there it would work reasonably well. There's another technique which is really rather clever, and that is to use a substance called 5-aminolivulinic acid, which sounds complicated. It's actually the precursor to the heme that you have in your body, which makes hemoglobin, right, which transports the oxygen. So in your body, there's a biosynthetic pathway which takes this, actually in the body it starts from glycine, the amino acid, and then travels on round to make the heme, which you need to plug iron into to make hemoglobin. So the last step in that process is to plug the iron atom in. And if you prevent that, then you produce a lot of material called protoporphyrin 9, which is a good sensitizer for PDT. So there are some treatments which use LA applied topically, for example, on a skin cancer, and you just wait a little while. It produces the sensitizer you want. The body produces it. You irradiate, and then the body disposes of it as well, because ultimately it forms hemoglobin. And so that again is just mainly used for surface tumors, but it's neat. And so there's a nice story you can tell there. And it's the story of the vampire. What characterizes a vampire? Well, the vampire cannot go out in the dark, all right? He's very pallid complexion, has very pronounced canine teeth, and so what are the people who suffer from this porphyria disease, what characterizes them? They have an excess of the porphyrin in their body. I mean, we deliberately engineer that in the cancer treatment, but people who suffer from the complaint have it naturally. So they can't go out in the light because they get absolutely fried by the sunlight if they've got all this porphyrin in their bodies. The effect of having this is for the same reason. They don't have the enzyme which plugs the iron into the porphyrin. So they have a deficiency of iron. And so they have this terribly pallid complexion. And of course, because they don't have the iron, their gums recede, and so they have very prominent teeth. So the legend of the vampire probably comes from people who suffered one or more forms of the porphyrias diseases. So all we have to prove now is that if they eat garlic, they actually will recover or die or whatever the legend is, you know.
Thank you. I'm conscious of the fact that some people have trains to catch, and I think we have tea and coffee outside. So can I, on everyone's behalf, thank our President for his excellent lecture this evening. Thank you, David.